Okay. So here, as we said, that S electron density is penetrating into the nucleus, that would be creating some Coulombic interactions that will help in changing the energy states. So therefore, that is related to the Hamiltonian. That mathematical equation is 2 by 5 pi Ze square psi square r square, where Ze is your nuclear charge, whatever the charge that nucleus is having. E into psi square is your electron charge density, and r is the radial distance from the nucleus. So this way we give the energy, and similar to that, we have one terminology. Okay, so when we said we have a ground state, we have an excited state. So due to the electronic interactions, Coulomb interactions, because of the penetration of S electron density into the nucleus, it goes to these states. So now this becomes E dash and new energy levels, that is E source. And similarly, if I'll say that goes as like excited state of my, that is E sample. So sample and source, they are not having same energies. Okay, at the concept of this S electron density penetrating into the nucleus, we understood that changes are happening because of the Coulombic interactions. So because of that S electron density penetrating into the nucleus, the radius of the nuclei, that what of the nuclei we are taking in excited state and ground state, they differ. They are not same. So there is one quantity with the help of which we can quantify the change in the energies of both sample and the source. So we have delta is equals to 4 by 5 Ze square r square delta r by r. This is sample and this is source. So this is an electron density at probability of finding an electron density at the ground state. So this factor is important because delta r and by r, it's the deviation in the radius. So what actually happens, delta r is the radius at the electron excited state and radius of the nuclei in the ground state. So generally, in case of the 57 iron, radius of excited state, the nucleus of the excited state, that is less than the ground state. So therefore, the delta R value becomes negative. So delta value comes as a negative value when we consider the 57 iron, whereas in case of tin, the delta R is positive. So it will just give you a sign. So this sign is important to tell you about whether the radius of your nucleus in the excited state and the ground state, they are having some difference, and which one is more, whether ground state radius is more or the excited state radius is more. We will take up this isomer shift and in full details in the next lecture. Up to this point, we have understood the Hamiltonian, the energy involved for having the transition from ground state to the excited state, to the excited state to the ground state. Why differences happen between the source and sample, even if we are taking the same source and sample, because of the electron penetration inside the nucleus happening. So is this clear up to this point? Then we can take up the assignment question.
Okay, ma'am, clear.
Okay. So I do understand there is a lot to grasp from the MOSFET spectroscopy, but this is an interesting topic. I hope I have covered almost all the concepts, and we'll try to solve the questions. If there is any other doubt, we can take up it in the next lecture. So the first question which you will try, the MOSFET spectroscopy deals with, the options are here: change in the electron spin states, nucleus spin state, or changes in the same nucleus spin states, or none of the above. What should be your answer?
Change in nuclear spin state, ma'am.
Because we need to have I equals to half to 3 half or 3 to half. It can't be in same nuclear spin state because it would be coming in anymore. Now try the second question. The nuclear state spin value of ground state iron 57. So we have given this mass bar active iron 57. So its I value in the ground state. What it is? Is it 3 by?
D, ma'am, 1/2.
Yeah, right. So when we have this naturally abundant iron 57 that is having I value of half, when we take it from the cobalt source, that radioactive source, then only we were able to have a 3 by 2. Now, third question, find the correct option or options for canonical conjugate pairs. These pairs which follow the uncertainty principle rule. So, energy and time, energy and momentum, x is space, that could be x, y, z, any translational vector into momentum or a space into time. So, which one makes the canonical conjugate pairs?
B option, energy and momentum, ma'am.
No, energy and momentum that does not make conjugate pair. What equation we had? We had delta E delta T greater than equals to H cross by 2. E option is right. And the main general example that for the uncertainty we take, that is delta X into delta P, that is space into momentum. So C and E option are right.
C and E option.
A and C option.
Okay, ma'am, A and C.
Okay. Okay. So the
Okay.
question, the energy resolution can be increased. We have energy resolution equals to tau by E. So this is energy between the two states and tau is the line width. This is your line width and this is your energy. And we know that line width tau is dependent on the time also. So this is the half life. So E is low, tau is low, then energy resolution would be high. Which option you feel is right?
Ma'am, once again explain, ma'am.
So energy resolution that we are asking for that resolution of that spectra, it has to be high only when it would be high. Whether this parameter would be high and this would be low, or it is low and this is high, what kind of combination is possible? The numerator has to be high or denominator has to be high or it has to be low. What combination? That is why 4 options have been given. So you need to choose the right option which will give you high energy resolution. So first you understand that energy resolution.
C option, ma'am. E is high, energy is high,
Just
tau
see,
is low.
firstly see the energy resolution. For any value, for example, if I have to have, say if I keep y as y, and if I'm having x1, x2 by y, x3 by y. Now my x1 is 10, x2 is 20, x3 is 30. So what do you think that P value, P could be anything. So P1 would be more for this, P2 would be more or P3 would be more. I have fixed the Y.
P3 value more.
Why? Because numerator is high, right? Similarly, now
Yes,
if I fix the X value, it is fixed and Y value, Y1 is 10, Y2 is 20, Y3 is 30. Now you tell me P1 would be more in which case?
Y3.
See it again. Now y is denominator. If I am having x by 10, x by 20, x by 30, x by 30 is x by 10 ka 1 by 3. That is even 1 by third of the x by 10. So if your denominator is less, you will be having more value or less value.
More value.
Yeah. You can understand it by this. For example, if I have x by 10, x by 100, x by 1000. So if I'm dividing certain part by 10 units, certain part by 100 units, and certain part by 1000 units. If I have, suppose, 1000 rupees. So if I have to give you 1/10 of the 1,000 rupees, that would be 100 rupees. If I have to give you 100 of the X value, that is 10 rupees. And 1,000 out of 1,000, that means I'm not going to give you anything. It's just a 1 rupee thing. So for 1,000 rupees thing, that X by 1,000, when the denominator is more, the actual value, that P value would be less. Similarly, in case of energy resolution, the numerator has to be high, denominator has to be low. So which one value, now which option is correct? I've given the answer also.
E E is a high, tau is low, ma'am. C
Again,
option.
again, you are reversing the situation. If E would be high, that is denominator. How your energy resolution would be more? Just see the formula also. Now, if energy is down, denominator, the way we did 10, 100, and 1,000. If more energy would be there, your actual value, energy resolution would be lesser because you are keeping it in denominator.
Okay, ma'am. Okay. Tau is high, E is low. B option, ma'am.
B option. And if this question could come in this particular format also, because tau is related to the half-life, right? So this is the half-life states. Say, for example, excited state. So if your tau is, if you want tau to be high, the delta T should be what? Low or high?
Low.
Why is it low? Because it has to go to the denominator to the right side. So when delta T, then
Yes.
half-life of the excited state would be less than your line width, the tau would be high, and when tau would be high, your resolution would be clear.
Clear, ma'am.
Now try the next question. The excited state radius is more than the ground state radius of for iron 57. This statement is true, false, we can't comment on it, or both the states have equal radius. We understood that because of the electron penetration, there is a difference in the radius of the nucleus, both in excited state and the ground state. So we talked about iron 57, the last formula, the delta formula. The delta R
A option is correct, ma'am. True.
just a second. Okay. So delta R we saw that E ground excited state, the radius and the ground state. Now what I said, the delta R is negative in case of Rn 57. Now tell me.
Ma'am, 1 second, tell ma'am.
Okay. So we saw this one, right? So we were having this formula where delta was there 4 by 5 ZE square R square delta R by R and psi square sample minus psi square source. That's the electron density that we are not looking into. So this delta R is the difference of, delta is the difference, that is radius of the excited state nucleus and the radius of the ground state nucleus. So we said that in a case of iron 57, delta R is negative, and in case of tin, delta R is positive. So if delta R is negative, so what do you think, which one is more? Excited state radius is more or ground state radius is more? So understand this as
Ground.
well.
Ma'am, ground state is.
Because if I'll say my excited state radius is 10 centimeters and ground state is 100. Now what would be the difference?
90, ma'am.
Minus,
90 centimeters.
right?
Minus 90.
Reverse the
Minus.
situation. Excited state is 100, ground state is 10, then delta R would be plus 90.
Plus 9.
Right? So when we have
Yes,
already
ma'am.
said that in case of iron 57, the delta R is negative, that means R excited state nucleus is less than compared to the ground state. So that's why the option here is false,
False.
right? Understood?
Right, ma'am.
Okay.
Understood, ma'am.
Now, try the sixth question. Out of S, P, D are 4 orbitals. Which one has finite probability of finding an electron at R equals to 0? So finding in finite probability, that means psi square has to be non-zero at R equals to 0. So we saw that RDF graphs. So out of 4 orbitals, which one is having the probability non-zero?
S orbital, C, ma'am.
Yeah. And the last question for this particular lecture is MOSFET spectra is a plot between which one? Is it transmittance versus wave number, transmittance versus velocity, absorbance versus wave number, or absorbance versus velocity?
Absorbance and velocity, D option.
No, really, actually, what we had is this graph, which I told also. So this is this one. The transmittance versus velocity is your final plot, which you will get in MOSFET spectroscopy. Because we
Okay, ma'am. Transmittance and velocity.
and ultimately, because our detector is going to detect only the transmitted light. So it depends upon the detector. If it is going to show the absorbance value, we can calculate the absorbance also. But actually, detector is taking up the transmittance value only. So whatever the amount of energy is being transmitted, that will only be able to show it. So depending on the detector, we will be getting a MOSFET spectra between the transmittance as and the velocity as the x-axis, and the velocity is having millimeter per second units. So that is also important. So understood up to this point? We can absorb transmittance into absorbance, but generally MOSFET spectra is the number of counts or transmittance versus the velocity. So the B option.
B option.
Okay. So
okay.
This is it for today's lecture. So I hope you have understood what we have talked about. I will just brief it again because we have 15 minutes, so I will just explain everything one by one. What we actually started with. So we have covered all the concepts, recoil energy, recoilless conditions, everything. So we actually started with the understanding of the MOSFET spectroscopy, that it involves the gamma rays. Gamma rays are the maximum energy that is involved in the electromagnetic radiation, and they involve the change in the energy stage. The nuclear spin state values, that means I equal to half to 3/2, 5/2, something like that. So here in this particular case, we need to have nucleus, source and the sample both to be similar, so that if the source is emitting some energy, that same amount of energy can be taken up by the sample, which it will absorb, and then we can see the spectrum. Now, generally what happens, because of the high amount of energy, it does not emit the same gamma energy. It actually loses some energy in the recoil form, because some direction, some amount of energy goes into the opposite direction as a kinetic energy. So whatever the sample is going to have now, that would be less amount which was required to have a transition. So that's why for the source, what it is emitting, that is minus ER, and what sample requires its transmission plus ER. The total difference becomes recoil energy of 2 ER. So that means this recoil energy will not let the source and sample to be in resonance to have the absorbance to occur. For that particular case, what we do, so this is a scenario when there is no overlap or zero overlap. And when absorbance is zero, there would be total 100% transmittance, and we will see a straight line. So what we do, we generally, Rudolf Mossberg, who was a scientist, while doing his PhD, he actually developed this, that if we put our source and sample in a solid matrix, we restrict their motion, so there won't be energy. Only there would be internal vibrations because of the, but there won't be any external translation. So that can restrict our recoil energy. So whatever the opposite direction that kinetic energy was being used, now it will, and therefore we have maximum over. So the recoil energy is given as that sum of translation energy plus.
Time 5 minutes. 5 நிமிஷம்.
Sorry.
இதுங்களா? Open ma'am.
Okay, so E translational plus E vibrational. So we had this condition. Now, even if we have the absorbance, okay, the source and sample are now being fixed in a solid matrix, so there won't be any translation motion. Now, why we say that absorbance and versus energy spectra looks like this way, not as a straight line, because there would be certain line width, which we relate by using the uncertainty principle. The way we have a space into momentum as h cross by 2, similarly, we have delta E into delta T. Delta E is energy between the two systems and delta T is the half-life of that particular state. And we can relate the delta E with the line width. That means the line width of that graph. If delta tau is very less, then that would be coming as a peak, like very sharp peak. So the line width is there, and line width is dependent on your delta T value. So this is a combination of line width, like how much width it is going to have, and delta T. So delta T is the half-life of the state. So these are the canonical pairs. So if we are taking a condition case of iron 57, there would be a transition from I equals to 3 by 2 to 1 by 2, that is having a half-life of 141 seconds. And from there, you can calculate the line width. So this comes as a line width. Now, if I'll talk about the resolution is the ratio of line width divided by the energy. And we saw that in case of the MOSFET spectroscopy, the resolution is coming to be very less, like minus 13 electron volt. So we can't see any kind of changes, or whatever the changes will happen, we won't be able to see because the resolution is very small. So to increase the resolution, we have to increase the tau value, that line width, which can only be possible when delta T, that half-life is less, and energy we have to lower down. So that will give you the proper and good resolution. After that, when we had, okay, so this has been explained like here also. Now we understood that gamma rays change in nuclear spin state and recoil energy, we understood. Now, the main thing is like MOSFET spectroscopy is not valid for every nuclei. There has to be certain criteria, and only few nuclei are there. They are called as MOSFET active nuclei, because for MOSFET spectroscopy, there has to be transition between the different nuclear spin states. And for that also, energy should be that much, which would give you proper resolution. If energy is very high, resolution becomes very less. So you won't be able to see any spectra in that particular region. So therefore, that they won't be called as a MOSFET active nuclei. So generally, we consider the two cases, iron 57 and tin 119. So in this case, now we know that in case of MOSFET spectroscopy, the source and sample should be same, but the source should be in excited state already so that it can emit some energy. So if I take iron 57, the most abundant form is iron 56, so which is not MOSFET active. Iron 57 is MOSFET active. So it is having an abundance of 2.14, and moreover, we have I state equals to half. If I equals to half is there, that means it's a ground state. It will not emit any energy. So there won't be any emission of the gamma rays. So how do we make our iron 57 as an excited, in an excited state and as a source? So we change the source from this particular three iron to the cobalt. So we take an actually radioactive, which is already in an excited state. So with the passage of time, it slowly converts to the iron 57 by capturing an electron. If it captures an electron, there would only be a less in count of electron number, but the mass number would be same. So we have this particular iron 57. Now iron 57 would be in the I equals to, cobalt would be in I equals to 7 by 2, that would be having very high energy. Then it goes to iron 57 thing, that is 5 by 2, that is also having a lot of energy, that 136.32 kilo electron volt. And the next state is I equals to 3 by 2, which is 14.4 kilo electron volt. So the energy difference is 122 kilo electron volt. And whereas 3 by 2 to 1 by 2, it's difference of 14.4. So you can compare the difference of 122 and 14. That's why that 122 region, the transition from 5 by 2 to 3 by 2, it is not going to be active in MOSFET region because energy is so large, the resolution becomes very less. So we can't see that transition. So only the transition which is visible, that is 3 by 2 to 1 by 2. Now from the cobalt 57, we got iron 57. That's the active source, which is already in excited state 3 by 2. And therefore we can convert and emit the gamma radiation, which can be absorbed by the sample. Now, how do we get this radioactive 57 cobalt? So it is formed from the iron 56 itself, which is highly abundant. So when it is using a cyclotron, when we bombard it with the deuterium, which is having mass number of 2 and proton is 1, so it converts 56 to 57 cobalt and loses 1 neutron, and this is the net reaction. So this is also very important. It generally being asked in net and gate exams also. So this where we got, okay, this is the journal equation, and finally we got that, okay, source is also active and sample is also ready, because sample is already in I equals to half the ground state and source is in I equals to 3/2 excited state. After that, we saw that, okay, when both are at the same energies and they are emitting in the energy, there would be 100% absorbance and no transmittance. Whereas our detector actually detects a transmitted light. So what do we do? In this particular case, absorbance would be hundreds and there wouldn't be any transmittance. So we will get a straight line. Now what we introduced, we had Doppler effect where we can fix the sample as well as detector, but we can move our source. When we move the source with the velocity, the energy of the sample and the source that changes. So how it changes? So we found that we put a wheel on the source so it can move towards a sample, that's a positive velocity. Away from the sample, that's a negative velocity. And with that, we get the released gamma radiations formula where it depends upon the velocity of the source and divided by the speed of the light. Now we saw the graph when both are fixed, nothing is moving, then there would be 100% absorbance and transmittance would be 0. Whereas in next case, we saw that this middle one, that's a case when v is equals to 0, that means velocity of the source is 0, it is not moving. So there would be 100% absorbance. If I move to away from the source, that would be minus v1 velocity, minus and positive, it's just the direction. So if it moves, there is a certain region where it is overlapping, that means there is absorbance, and we can expect at this particular absorbance, there would be this much transmittance. If it moves away from that sample with minus v2 velocity, it will have no absorbance because there is no overlapped region, therefore 100% transmittance. Similarly, it happens when it moves towards the source, towards the sample, with v1 and v2 velocity, we got the similar. When we jot all the points from minus v2 to plus v2 going through the v equals to 0, it forms a v kind of curve. That's a curve between the 100% transmittance as well as the velocity. That's your actual MOSFET spectra. And even if we have the source and sample same, why do we say that their energies so released and absorbed are different? Because the electron density interaction with the nucleus is different at excited state at the ground state. First condition is electron density to affect the nucleus, that Coulomb interactions for that particular thing, both of them have to be in a similar region. That means electron density should penetrate into the nucleus, only then there will be some interactions. And then with the help of the radial density wave function, we understood that in case of the s orbitals, be it 1s, 2s, 3s, there would be certain psi not equals to 0, that probability of finding that electron into the nucleus, that would not be 0 when r equals to 0. That means radial distance from the nucleus is 0. That means it is staying at the nucleus. So when that happens, only the s orbitals, they have the tendency to penetrate into the nucleus, and because of that electron nucleus interaction, there is a transition of the energies, and we saw the transition in this particular format. Okay, earlier it was the condition, and after the Coulomb interactions, the energies got higher because now it's an unstable system. And that would be different for source as well as sample. And based on that only, we get the different Hamiltonian, that is energy. So that depends upon the nuclear charge and the charge electron density. And ultimately, we saw that for different nuclei, delta R by R, that is the isomer shift, delta R by R will define you whether your delta value has to be negative or positive. This we will take up in details in the next lecture. So, is there any question, whatever I have covered so far?
Okay, ma'am, I understood.
So, I hope that I tried my level best to complete and clear, make you understand this thing. If there is any doubt, anything, if you don't understand, I would request you to go back and see some radial wave functions. of different orbitals. Then you will see where the node is occurring, whether the psi square is 0 or not. You will be easily able to find it on the Google. So see, because we have taken the case of p orbital and s orbital, we have not taken the case of D and F. You can go back and check the D and F also, where you will see that okay, the psi square is 0 at r equals to 0. So that's why D and F also they don't penetrate. So that would be a good question. There could be possibility of having a question in the exams also. And based on that, there would be a signing question. So you can go back and attempt them. If there is any doubt, you can come back anytime in the next live session. So if there is any doubt, you can still ask me. If not, then you can leave this session. Any further doubt? Okay, so if not, we will end up this session here. Week 9, we will be taking up more detailed concepts of the MOSFET spectroscopy. We will be taking up different nuclei, iron in different oxidation states, and we will be explaining with more examples. So I hope you guys have understood the concept. Thank you for joining the live session. Hope to see you next time soon. Thank you.